now we're going to analyze each of these three components in turn. First of all, I'm interested in the seasonal cycle and ideally what drives that. Now, one of the problems is the data doesn't often have all the years. Some months might be missing. And what I'm going to do later on is use the reshape function to kind of reshape my data into sort of each month, and then I can sort of average it out. But what I need to do first of all is sort of just find the years when I have all months of data. So what I'm going to say is year month f. I'm going to use the floor function. This is like the round function, but it floors everything down. So I go from a decimal year essentially to a year, and you can see the first one does have 12. And we can go through, and this last one also has 12. But some data sets that we might plot later won't have 12, and so the code won't work. So I want to make sure that we only find years that have 12 months. Okay, what I'm going to do now is use the group counts function on the YMF, and that's going to basically tell me which months, which years have 12 months. You can see that one has 12, that one has 12. We can scroll down, so actually we have 125 years with 12 months, which is really, really good. Okay, then I'm going to go down and find the unique ones, so we can do unique YMF. So this should actually give me 125 unique years. So here are all of the unique years. Okay, now what I'm going to do is just find the ones, sorry, I keep on plotting these in the wrong boxes, getting a bit ahead of myself. I'll put a subcolon in so it doesn't put it to screen. Okay, now what I'm going to do is find just the unique ones where G is equal to 12. Okay, so actually all 125 are equal to 12, but there may be some data sets in the PSML, I don't know, there's definitely some, and I think I'll suggest them to you, one to you later, where that isn't the case. Okay, now I'm going to create a variable called I that shows where the values of U are present in YMF. So we say I is member YMF and U. So this tells me which rows kind of correspond between the unique ones. And then what I'm going to do is I'm going to create a second variable called C, SMSL, seasonal cycle, and it's basically just the seasonal cycle line. Now in this case it's all of them, but again, when you have a data set where there is some years without 12 months, it won't do. And it all comes down to this kind of point that I want to do here, which is reshape. So first of all, I'm going to find the length of C SMSL. So it should be 1500. And then what I'm going to do is I'm going to use the reshape function. And I'm going to say reshape. So at the moment, this seasonal cycle is just one long column of data. But what I want to do is I want to reshape that variable. We can just overwrite that variable into, I want 12 rows, and I want 1500 divided by 12 columns. So I've converted it into a matrix here, where essentially each column is a year. So this is year 1, this is year 2, this is year 3. So column 1 is January, February, March, April. So now I can take a mean. So I can say my monthly mean is the mean of CSMSL, and I'm going to go down the second dimension. So it's going to go, it's going to take a mean of each row, and I'm just going to emit nan, or else it will tell me. So basically the mean of January is minus 166, the mean of February is minus 133, just check I've done that the right way, yep. So each of these now is a mean. So the mean of December is minus 6. So this is the kind of average seasonal cycle. And we're going to plot this. But just before we plot it, we are going to work out the minimum and the maximum. So we can do the max of mm, and I'm going to call that mm max. I'm going to find the row number when there's a max. So the maximum is 130 and it's in month 6, which is June. And then I'm also going to do the same, but I'm going to do a min. I'm going to call this J. Notice how I just cut and paste. And the min. So the min, so actually the seasonal cycle peaks in June. Troughs is maximum in June and is minimum in October. Okay, now what I want to do is just save that variable to a table, just because it's nice to store it in a table. So I'm going to store the max and the month when it's maximum. I'm going to store the minimum height and the month when it's minimal, and then I'm going to store the range, the difference between the two. So it's the max minus the min, and I'm going to give these variable names. We can give it some nice names now. I'm going to use the funny brackets to separate out my, so I've got 5 variable names here. So I've got the max amplitude. I'm just going to put these 3 dots here to put it onto a different line. So I've got the max amplitude, and then the month of max. I'm going to have the min amplitude of the seasonal cycle, and then month of min, and then I'm going to have the range. Actually, I could have cut and pasted that from there. Okay, so now you can see the data in a nice table. So the range is actually 21 centimeters, so 213 millimeters. Okay, so now we can produce a figure to plot this. And again, I'm just going to go up to the top and nick this code and just cut and paste it here. Now we only need a 1 by 1, so we can get rid of that. Okay, so the first thing that I'm going to plot is all of the seasonal mean sea level cycles, and I'm going to plot this as a grey. So I'm going to put a colour is 0.5, 0.5, 0.5, and I'll show you what that looks like in a second. So let's just run that. So those are each year. So each year you can see, so it's basically taking each of these years but overlaying on the top. So some are higher, some are lower, but you can see that very strong seasonal cycle there. And this is due to the strength of the Lewin current that comes down the coast here. When the current is strong, the seasonal cycle is higher. When the current is weak, it's also due to temperature. But what we can do now is we can plot the month one as red, and here I'm actually going to make it the line width a bit thicker. I'm going to plot it as 2. So let's plot that on. So now you can see we've plotted the line on. That's the mean that we calculated, this mm. And then I'm going to plot the maximum level as a blue circle. What mistake have I made there? Oh, sorry, I did a minus rather than an understroke for the variable name. That's a bit hard to see, so I'm going to say marker face color blue. The color just is the outline, so you can see that blue dot there. And in fact, we could actually make the marker size a bit bigger if we wanted to. 10. Okay, I'm going to cut and paste that code. Always cut and paste. This time I'm going to plot the minimum. I need to plot this against J. Again, you can see it tells me what the error is. There's an unrecognized variable, which normally means I've spelt it wrong. Okay, now what I'm going to do here is set the xlim. Need square brackets because two numbers are going to go from 1 to 12. I'm going to set the x ticks as going from 1 at intervals of 1 to 12. So now you can see that looks much better. And then finally, a nice little thing is I'm going to set the X tick labels. And here I am going to use, so here I'm going to say Jan, Feb, March, April. Notice how MATLAB is filling it in for me, the June, July, August, September, October, November. Oh, put the wrong ones, double quotes. And then December. Normally I like to keep everything in the same order, so I tend to do the X labels first, title, then the exit, then the grid, then the font size. Okay, so now you can see it peaks, it troughs in October, peaks in June, and that is very much strength. And if you were to pick another site further up the coast, or further down the coast, further up the coast, you'll see that actually it peaks early in the year. So I encourage you to do that at the end. Okay, now we are going to look at the interannual variability. So we'll look at this blue component and see what drives that. Here, this is very much determined by the Lewin current. Okay, so now we're going to use data from the Southern Oscillation Index, which is stored at the University of East Anglia. So we can go to that website there. Try that again. I just cut and paste. I don't know what's happening with my computer. Sorry. Okay, so the Southern Oscillation Index is a measure of how strong ENSO is, and you can read more about it here. Essentially, it's an atmospheric pressure difference between Darwin and TET, but when it's strong, it's La Nina, when it's weak, it's El Nino, or one of the other. But what we're going to do is scroll down here and download this SOI.dat. And you can see that it's a year, and each of these is a month, so it's the strength of the index in a month. So I'm just going to right click on it, download the file to that folder. Make sure it goes in your data folder. So keep everything nice and separate. Okay, again, we can open that DAT file. It's just an ASCII, so it's a text file. So we can see it goes from 1866 to 2022, so it more than covers the data we want, which is nice. Okay, so first of all, we're going to load in the data. I'm going to call it S. Again, you can use the import data function, and then you can give it a file name. I'm not going to hard code this because we can I'm going to hard code this because we can use the SOI. There's only one value, so even if there's multiple sites, you'd still correlate it with the same index. Okay, so we've loaded in the data there. Okay, what I'm going to do now is find this data is longer than my other data, because this data starts in 1897, whereas the SOI data S starts much earlier, 1866. So what I'm going to do is I'm going to say S year, the start year, is YMF. Remember, F was the floored, the rounded, so that's the start year, is 1897. And then I'm going to find the end year. Again, I don't hard code this because if we download, and here we can just use the function end. So it goes from 1987 to 2021. So what I want to do is basically just keep the data in those years. So I'm going to say S rather than all of the S. I'm actually going to delete some. You can use the square brackets there. I'm going to say S shift column 1 is less than the start year, or, which is this vertical line, S shift column 1. Basically, this is just kind of finding the row numbers, is greater than the end year. Okay, so here S is 157, but if we run this, we'll see it deletes S now. Oh, I need to put a comma and all the rows, so it's just the row number. So now you can see it's gone down from 157 to 125, so it's just from 1897 to 2021, which is the same number of years I have with my data. So now I can do a direct comparison. Okay, now I'm going to use the reshape function, similar to what I did with the data. So I'm just going to find the length of S. Actually, it should be the same as the length of the other one, 125, so I don't actually need to do that because I can just use the other one, but I will. And I'm going to say SOI, I'm going to do big is reshape, and I'm going to reshape S, but I'm going to reshape all the rows, but just column 2 to 13. And I'm going to prime it, which kind of inverts it. And I'm going to reshape it into an L, because at the moment it's in 12s, but I actually want it as one long column, so I can compare it to my interannual here. So I want to take it from 125 by, well, I want the first 13. The 14th one is, I think, the average, the annual average, but yeah. So I'm going to go from rows 2 to 13, I'm going to prime it, and then I'm going to reshape it. So this should turn it into a nice long row for me, and I want it into one column. Okay, so now I have this SOI, you can see here, which is the same length. I'll just delete all of these variables, but it's the same length as ISN. So, yeah. Okay, I hope that makes sense. Okay, now remember I used a moving mean up here. In fact, we could probably cut and paste the text. Remember, I used a moving mean to calculate my seasonal cycle. So because I did a 12-month mean on the seasonal cycle, I really want to do a 12-month mean on the SOI as well. So I'm going to call it SOI A kind of for annual. I'm going to do the SOI, and I'm going to do 12-month mean, and then I'm going to omit the nan again. Okay, so now I should be able to directly compare the two. Okay, so what I'm going to do now is plot this, and again, I'll just nick the text from a previous figure to save me having to do it. I'm going to plot a 1 by 1, but this time I'm going to do something slightly different. I'm going to hold on, just get rid of that. In fact, I'll just get rid of everything for the time being. Hold on, what I'm going to do is I'm going to set this on 2 axes. So I'm going to do the y axis is left, and here I'm going to plot ym against my sea level as blue. I'm going to make the line width 2. Okay, I'm going to add, actually I shouldn't have deleted my X, Y and label, but let's bring that back in. So this is going to be on the left hand side of the axis, so I'm going to do year and level millimeters. Now I'm going to cut and paste that, but this time I'm going to change it to the right. I don't need an X label again because I've done that. Now this one is the SOI. Now on the right hand side I'm going to plot now my SOI smooth, and I'm going to plot it as a magenta line. So actually this colour here, just so it matches, I'm going to change that colour to magenta. I'm going to plot a box on and grid on. Let's see if I've done this right. Okay, so there's the 2 lines. So you can see on the left side I have the interannual sea level, on the right I have the SOI, and you can see actually they agree very, very well. When one is high, the other is high. When one is low, the other is high. It's not perfect, but actually the correlation looks very good. So it shows you that ENSO is driving this variability like I discussed in the lecture. And then finally, I can use my user function called correlation coefficient, coefficient. What I can do is I can put in my interannual mean sea level, put in my SMI. I'm going to use the word rows complete. You can read in the help menu while I do that, and I'm going to go CC is the correlation, and P tells me if it's statistically significant or not. Yes, you see, it's very handy. If there's an error, you can actually click fix. So actually the correlation here, it gives you a 2 by 2 matrix. The correlation is 0.6, which is actually very high. And because this number is small, it's statistically significant. So you can see that the Southern Oscillation Index is driving something like 60% of the variability here, which is really, really quite strong. And again, it's interesting to see how that strength compares as we do other sites around the coastline. Okay, and then finally, we're going to calculate linear trends for different periods. Now, with linear trends, unfortunately, the polyfit function, you can only give it data that doesn't have any ends. So what I'm going to do is I'm going to create a new year-month variable. I'm going to call year, and I'm going to create a new relatively mean sea level variable. But what I'm going to do is use the isNan function to find the data in relative mean sea level that is n, and then I'm just going to get rid of those rows and get rid of those columns. I don't want to do that for the plot because it doesn't look very good, but for the data I can get rid of those. Okay, I'm just going to put a semicolon on each so it doesn't print it to the screen. Okay, so now I have this relative mean. So you've got lots of variables going on. It can be quite confusing, but this one now only contains good data. There's no NaNs. Okay, and then what I'm going to do is, let's call it T1, is I'm going to use the polyfit function to fit the data as to all of the period, and 1, remember, is a linear trend. So again, I'm getting a trend of about 1.7 millimeters per year there. So that's the T1. Yeah, 1.7 millimeters per year. This is the intercept, which is less important. Okay, now I'm just going to fit the data to the period 2000 onwards to see if the trend is getting faster more recently. So I can say I is find me the rows that are greater than the year 2000. So it'll be zeros, and further down you should see ones. And then this time I'm going to copy the polyfit again. I'm going to call it 2, but this time I'm just going to feed it the row i's and a 1. So here now you can see the trend has gone from 1.7 up to 3.9 up to 4 millimeters per year. So the trend is twice as high, which shows you that sea levels are accelerating. And then finally I'm going to do a quadratic for the whole period. So I can go back to this original data set. I'm going to call this T3. To do a quadratic, it's just a second order polynomial, so it's 2. So this tells me if it's accelerating. Now there's three turns. So this one is the acceleration. So there's an acceleration of 0.049 millimeters per year. So it is accelerating. The trend is getting faster and faster, but it's relatively small. But accelerations are always small numbers. Okay, and now the final step is to, I seem to have lost some code here. The final step now is to do a plot. So what I'm going to do is, first of all, generate some trend lines. So here we can use, like we did before, the pol val with T1 and YM2. That's the... Now for the second one, I'm just going to give it the I rows, because remember it's only since, and I need to change that to 2. And then for the third one, so these are just generating lines that I can plot on a graph. I'm going to do a T3. Okay, so this has given me 3 lines corresponding for the trend, linear trend for the whole period, linear trend for 2000, and then a quadratic trend. And now what we're going to do is produce 3 plots. So I can go up here, and I can actually get this, steal this, to generate our figure. We're going to have 3 figures. Okay, so I'll come back and do the titles in a minute, but let's just plot the data first. Okay, so what I'm going to plot is YM2 and the relative mean sea level 2 as a black line. Let's make this line width 2. So that's the kind of raw data, but on top of the raw data here, I'm going to plot the line that I plotted as magenta. So it's going to be year, or well, you could change that to date level. And then for the xlim, I can put the start year and the end year. Okay, so let's just plot that and see what it produces. Okay, so there you can see it's plotted the data and that kind of trend going through it about 1.7 millimeters per year. Now what would be nice is to have a title, so let's add a title, but this time I'm going to split it up. So I'm going to say A is linear rise over the whole period. And what I'm going to do is I'm going to actually bring it, I'm going to use the num2 string function to bring in T1 and row 1, column 1, because that's that first value. Just want to bring in this value, the 0.7. And I'm going to round it to 3 decimal places. And then I'm going to bring in some quotes here, and I'm going to say millimeters per year. So this should now give me a title. There's an error, so that's a workable one. You can see unrecognized function, so it just means I've spelt it wrong. Okay, there you can see linear rise as put 1. Again, I haven't hard coded it because if I change this site, I could have just written 1.7 here, but I haven't, because if I change this site, I want it to update the data. Okay, on the next one, I'm going to plot the data, but this time just the data since the year 2000, which I've stored in these I rows. Remember, we've got I up here, and this time I'm going to plot L2. Oh, sorry, wrong one. Make sure you do the right plot. I, and this time it's L2. Let's put in the title again. Now here, this is going to be B. This is the linear rise since the year 2000. And this now I need to change to D2, so let's run that. So this should just plot the more recent period. Okay. Now, I need to put an I here. Remember, I only ran that for... Okay, so there you can see that is the linear rise, but just for the more recent period. Now what I can do actually is I'd probably set the X limits to be the same, just so you can kind of directly compare them. Okay, so you can see that the trend has been much higher, 3.9 millimeters since 2000. And then finally, I'm going to plot the quadratic trend, which is the acceleration. So here, this is quadratic rise. Oh, don't know what I did there. I seem to press something by mistake. Let's just run that again. Okay, now I can change this to quadratic. Probably haven't spelled it right over the whole period. And this is T3. Now you have to be careful here. This is millimeters per year squared, because it's a rate. I'm just going to use the X lim and Y lim again. Now this one, it should be a slight curve on, and you can see there is a slight curve that's getting faster and faster, but it's a bit hard to see. Some of the other sites will have a more rapid acceleration. Okay, so that's the practical done. And you can see that actually we've done a really advanced analysis here. We've looked at the seasonal cycle, we've looked at the interannual variability, and that's driven by ENSO. We've looked at a long-term trend here. Now what I'd recommend now is to download some other sites. So for example, you could download Albany, which is 957, so we can go back to the permanent service for mean sea level, go back here, order this, but now we're going to download 957, which is Albany. So this is a site further down the coastline. So I'm going to link on that file. Again, remember to pop it in the data folder. So now what I can do, and this will test my code and see if I've done it well, I can just go up here. All I need to do is change this, nothing else, 957. I can run it again, and this will produce everything for that site. So you can see just how powerful MATLAB is now. So you can see this site is very different. The data is a lot shorter. We split it into 3 components. Again, there's a strong seasonal cycle. But let's have a look at it. you can see actually the seasonal cycle is later than is quite different. It's the trough. Previous was in October, now it's January. The correlation before was 0.6. Here you can see actually the correlation is now 0.8, so it's actually higher. You can see the trends before were 1.7. This now, the trend is a little bit different. Here, sea level seems to actually be decelerating rather than accelerating, but I think that's because it's a much shorter, it's too short a record. And again, you could look at another site, so for example, Exmouth, and do that. Okay, so I hope you enjoyed that practical, and now you can see actually you could, potentially, there's over 1,500 sites here. You could actually use all of them now, and you could actually run this script multiple times. In fact, you can convert it into a function, do that automatically, and I'll show you that next week. Okay, goodbye.